Alright everybody, welcome to our Math 20-1 playlist on sequences and series. We'll talk a bit about what that even means, the difference between them, different types, arithmetic, geometric. We'll talk also about the infinite cases as well. So let's get into it. We'll start our first lesson. We'll start talking a little bit about arithmetic sequences and what that even means. So consider this following sequence that you see on here. 4, 7, 10, 13. There's a pattern, and we're going to just take a look at the next few terms. So if you think about going from 4 to 7, one of the ways you can do that is by adding 3. 7 to 10, same rule applies, add 3 again. 10 to 13, it also works. So it seems like a reasonable assumption that our pattern here is just to continue to add 3. So our next couple terms then, let me figure out what color I want to use. Let's use blue. So we'll use 16, 19, 3 more after that's 22, and I mean, we could keep going, but we'll see that as long as I keep adding 3, the pattern stays the same, and I'm just going to keep increasing. So we'll express this arithmetic sequence as a table of values. Okay, we'll graph it just to see what it looks like, just to give us some background information as to, what these kind of look like. So we'll make a little table of values here. I'll put n on one side and tn on the other. We'll talk about what those mean in just a second. So n is going to be, as you can see, you've got a list of definitions down below, and even on the other side here too. So n is going to be our term number, tn a specific term value. That's important to denote that distinction. So maybe let's add that on here. N is going to be, what did we say, a term number? Okay, Tn, what we get out of that is going to be the term's value. So for example, if we use n as, well, 1, this will be term number 1. So in that pattern that we saw, that sequence, the value of that term was 4. Very similarly, when you did this in Math 10, you talked about functions, inputs and outputs, independent variables and dependent variables. This has, some of those features in there as well. So our term number is number 1, and the value of that first term is 4. So our second term is 3 more than 4, so the second term's value is 7. You can keep on going. We'll give us a couple points here. So the third one was 10, the fourth one was 13. Extend my table. 5 and 16, 6 and 19. Seventh term had a value of 22. Now, obviously, with the grid that I have here, well, we don't really get all the way up there. Which is fine. We're only going to put a couple on there to graph it. Really, we only need 2 points to see what this graph is going to look like. But our first term had a value of 4. So let's just graph this. So let's say that, well, our input value is n, our tn is our output. So x you can think about as being your term number, tn as being your y's, in order to give us a way to graph this. So if n is 1, tn is going to be 4. So your first coordinate pair at 1, 4, and you can see that dot in there. We'll do a couple others. 2, 7, so that's 6. This should be 2, 7, and 3, 10. 3, 10. Okay, so you can see that this essentially is going to represent something that is linear. And as long as you have 2 points, you can draw the line that exists between them. But think about why I may not want to draw that line. Right, we'll talk about it in a couple minutes here, but think about what it might mean to connect them. Right, think about what it might mean if that line went into the negative parts of your graph. What does that mean? So I'm going to leave just these 3 dots the way that they are, and I'm going to choose not to connect that line. So keep that in your mind, think about it, and we'll talk about it as we get into some of the things here. So an arithmetic sequence, that definition that you see there, says it is a set of numbers in which you get each term by adding a constant. And that is the exact same definition. Maybe one word's a little different when you talk about a linear relation. Okay, linear relation is very similar. So take a look at our table of values and what we did. From 4 to 7, we added 3. 7 to 10, added 3. 10 to 13, added 3, so on and so on. Every new term value is obtained by adding the same constant. And that constant's very important. It allows us, well, if we know what it is, and I know where my pattern starts, essentially I can find out what any term value is. I don't have to keep adding that constant. We can logic our way through this, and we can come up with any number we want. Okay, that number that you keep adding, that constant, is called your common difference. Okay, it's the constant you add to get consecutive terms. And if you aren't explicitly told what it is, you can calculate it by subtracting a term with the previous one. So think about this, right? If I had 19 and 16, but I wasn't told that the difference between them was 3, I even said the word difference, yeah, it means subtract. So you can take those two terms, subtract them, find out how much bigger one is than the other. Okay, so you could do that as well. You could calculate it. Okay, take any term and subtract the one before it. So 22 minus 19 is 3, 19 minus 16 is 3, whichever ones you want. We'll also talk about finite sequences, right? Sequences that stop at a finite point, or infinite sequences. Maybe there are some things that continue forever. What does that mean? We'll talk about that too as we go further into our unit here. Okay, a couple other things before we try some examples. An arithmetic sequence is something represented by a linear function. So we graphed it, we saw what happened, and you saw that graph was linear. And it's linear because it forms a straight line on that graph. The slope is going to be your common difference. So if you think about slope, and I'll scroll back up to my graph here for a second. If you remember slope, it was essentially how the ratio of vertical change to horizontal change. So the change in your y values versus the change in your x values. So think about this first point we graphed at 4, right? If I go up 1, 2, 3 units, well, there's my rise, right? That rise is plus 3, but 1 unit to the right, well, that's plus 1. So you can think about your slope as being rise divided by run, where the rise is 3 and the run is 1. So that slope here is 3, which is the same thing as your common difference. Right? So 3 over 1 gives me 3. That's exactly what we talked about before. So you could calculate it if you had a graph as well, knowing that it's linear. When you have that arithmetic sequence, remember there was 2 kinds of slope, which we even talked about. It could be positive, could be negative. The one we talked about earlier had all the values of the terms getting larger, so our slope was positive. Well, what happens if they were all getting smaller and smaller and smaller? Well, then my common difference would be negative, and I would be adding a negative each time. It's more difficult to think about it as subtraction, right? Think about it as adding in a negative for this context. Why are our x values always going to be natural numbers? Right? If you think about the graph we did, we said that our x-axis represented the term number. So that was our x values. Right? So this is going to be term number. Natural numbers are your counting numbers. Right? Those are going to be your counting numbers excluding 0. So your counting numbers like 1, 2, 3, 4, 5, so on. Why do they all have to be natural? Well, think about having a term number that's negative. Does that make sense? I'm not going to have a negative second term in a pattern. And, well, we're not going to really talk about this in terms of term 0, right? This pattern has to start somewhere, and that will start at the first term, which comes in our, the first number in our natural number set. So negatives don't make sense. No negative term. Now be very careful with what I'm saying. It's not that we can't have a negative term value, right? Term number 1 could be a negative number, but I'm not going to have term number -1. Okay, the value of a term can be negative. The term itself, like my term number, can't be negative. That's an important thing to note as well. Okay, what sequence would you have if the common difference was 0? So let's just create a pattern. Let's just create a sequence. Well, let's say my first term is 2. If the common difference is 0, well, think about doing, as your second term, 2 plus your common difference of 0? Well, you'll end up with just 2. Same thing again. 2 plus, well, the common difference from the first time to get there, plus another common difference to get to the third term, it's still 2. So you're always going to have a term value of 2. So what sequence would you have? This would be a constant. There'd be no change. Since that common difference is 0, nothing is being changed. Okay, so let's take a look at some more kind of specific examples relating to this. So using some of that notation, stuff we talked about, we'll make it a little bit more explicit here. This will assist us in making a formula to even calculate any term. So there's those definitions. So T1 is what we'll call the first term. N, like I said earlier, the term number. D is the difference, so that common number we're adding to each value to get the next successive term. And Tn, what that specific term value is. So up in the table above that you see here, all the term numbers are filled in from 1 to 5. Their values alongside them. So let's translate this into 20-1 language and using those definitions. So if 2 ends up being the first term, we need to go represent 5 as well being the second term. And what we can do is take 2, that was our first term that we had. If we add our common difference to it, we're going to end up with the second term. It's going to be 5, right? Term 2 is going to be 5 because that's what it says up above. That's the value that we had. Okay, so that's 5. So right now we could solve for that common difference using that purple equation. Our common difference is going to be 3, right? 5 is 3 away from 2, 8 is 3 away from 5, so on and so on and so on. So I know that common difference is 3, and I could figure it out by just even writing add 3 in that table above, right? Pretty obvious to see it, but let's think about this in terms of building a formula. So down below, our third term then is going to be, well, whatever our second term was, adding in one more common difference. So my second term was 2 plus that common difference, but if I need to get to the third one, we're going to add one more. So add another common difference to keep the pattern going, and this works out to be 2 plus 2 common differences. I've just added another one. I think you can see the pattern. In order to get the fourth term, we'll take our third term, the one previously, and add an extra common difference. So for the fourth term, we're going to take whatever our first term was, add in 3 common differences. And now notice something. If this is the fourth term, I'm adding in 3 common differences. If this was the second term, I added in 1 common difference. If this was the third term, I added in 2 common differences. It's always 1 less than whatever term you're working with. And it's always 1 less because you're already starting with the first term. Right? You're starting from a consistent place. But then you're just going to keep adding to get the next value. So it might help to see it represented out like this. 8, 11. Now 2's not going to change, right? But 5 has changed something in our pattern. It's the same thing as 2 plus 3. So I'll use green to do that one. I'll use red for 8. Now 8 is the same thing as 2 plus 6. And orange for the last one. 11 is the same thing as 2 plus 9. And you can see that those other numbers that I've added are going to represent how many common differences we're going to have. Right? So for 5, we're starting with a 2. That was our first term. Adding in our 1 common difference of 3, that's how we got to the next one. But for 6, 6 is the same thing as 3 plus 3, which is also the same thing as 2 times 3. Right? We're adding in 2 common differences. 9, same thing, 3 plus 3 plus 3. In other words, 3 multiplied by that common difference of 3. So you can keep this going for literally forever, but what you're going to notice is it's always 1 less than whatever term number you're working with. So if I don't know how far I'm going to go, let's call this Tn. This could be any term. Well, what this is going to mean for us is our formula will say take the first term, add to it a number of common differences that's always 1 less than your term number. Since my term number is n, well, the number of common differences I'm going to add is 1 less than that. In other words, n minus 1. That formula right there will allow us to calculate literally any term number in any arithmetic sequence. As long as I'm adding a constant to get to the next one, this will work. Okay, that's what it's trying to tell me. So even if you flip this over, you'll see it even says the general term of an arithmetic sequence. So there's the format. General term is Tn, any term you want, is equal to the first term plus n minus 1 common differences. Right, so whatever that, you can see this one of two ways, so I'll rewrite it the other way. So Tn equals T1 plus n minus 1 common differences. Right, that's the other way you could see it. It means the same thing. I just moved, that variable to the back. They're still beside each other, means multiply, nothing is any different. So let's see if we can use this to calculate some things. For this arithmetic sequence, 3, 10, 17, 24, determine the 15th term, right, the value of it. Now you don't want to sit there and keep adding over and over and over and over and over. It's a very junior high way of doing things, right? Especially what if we were asked to find the 102nd term, right? You don't want to sit there and plug in your calculator 101 times, right? Very, very difficult and time consuming. So let's determine this, and you'll write down our formula first. So Tn equals T1 plus n minus 1 common differences. So we need to know a couple things here. I'm looking for T15. So for any of you that have taken physics, it's helpful to list things out on the side that you know. So T15 is what I want. I know the first term here is 3, and I can calculate that common difference pretty easily. Right, I'm going to go from 3 to 10, which means I'm going to add 7, double check the other ones to make sure it actually works. So for each time we're going to increase by 7. So there's our common difference. D is 7. And we've got everything we need, because Tn is what we're going to look for. Right? The n could be anything. We're going to make it 15. Right? So we're going to be looking for the value of the 15th term when the first term is 3. Now, the 15th term, its value is represented by Tn. That term number is 15, right? Those n's are the same thing, right? So 15 minus 1 common differences. So the first term's already accounted for. So in order to get to the 15th term, I need to include 14 common differences to get there. That's what this says, right? 15 minus 1. What did I forget? Oh, the common difference is 7. There we go. Right, so I need to account for 14 times we're going to add 7 to get to that 15th term is what this says. So we can do the 15th term calculated pretty easily as 3 plus 14 multiplied by 7. So our 15th term, which I'll add up here, our 15th term is 101. Right, so if you take 3 and add 7 to it 14 more times, you're going to get 101, is what this says. Okay, so that's pretty nice, that's pretty straightforward. Part B asks you for which term in that sequence has the value of 220. Which term is it that has the value of 220? So if you think about what it is we don't know, we actually don't know what term has a value of 220. I know that's what I want to get. I know it's going to be some term value. The issue is I don't know what n that happens to be. I don't know how many times I have to add my common difference. That's what we're going to try to find. So we use the same formula that hasn't changed, right? Our Tn equals T1 plus n minus 1 common differences. Right? I don't really know that, but I can plug in what I do know and find out what's missing. So Tn, that's the value this time. It's different than last time. I didn't know the value, but I knew the term number I wanted, but now I know the value. So we'll put that in. 220 is what I wanted this to be equal to. The first term is still 3. They're linked. Plus. N is what I'm trying to find. I want to find what term number makes this 220 possible. Common difference still 7. Now I've got a pretty straightforward equation to deal with. So the 220 is going to stay. There's my 3. This is equal to, or let's distribute the 7 into the brackets. So 7n minus 7. Collect all your like terms, and you'll end up with 224 being equal to 7n. Very, very easily now, divide both sides by 7. and you will find out that n is equal to 32. Okay, so what this means is it takes 30, it's the 32nd term that has a value of 220. So if I started at 3 and I added 31 groups of 7, I would end up at 220, right? It's always one less when you're adding in those common differences. Okay, so this means, so therefore, term 32 is 220, right? Term number 32, there's my value, 220. That's what we found. Okay, what happens if I'm not told where I start and I'm just told two values? Right, what do I do then? So two terms in this sequence are, well, the fourth term is -4. The seventh term is 23. What's the first term? And the key here is remembering that it's arithmetic. So what that means for you is, well, if it says arithmetic, I know I'm adding a constant each time. So from 4 to 7, I'm adding some number 3 times, but it's the same number. Right? Even though these terms aren't side by side, think about subtracting them. The difference that you find means, well, it should be divisible by 3 because you're adding that difference 3 times to get from, well, term 4 to term 7. We're just skipping 5 and 6 in between. So let's make this a little bit more formal. So term 4 and term number 7 are 3 apart. Right, they're 3 apart. So this means we could do, in order to find our common difference, we'll take the 7th term, subtract the 4th term's value, cut it into thirds. Whatever I get should be divisible by 3 because I have to add that number 3 times to get there. So my 7th term, I'm told that value is 23 minus -4 divide by 3. Well, 23 plus 4 is 27, divided by 3 is 9. Which makes sense, so test this out. If you start at, you can grab a calculator, right? If you start at -4 and you add 9 to it one time, you get 5, add 9 a second time, you get 14, add 9 a third time, and one more. What did I do here? Did I add something wrong? -4 plus 9 plus 9 plus 9. I'm good. 23. So I had it the first time, I was just thinking about 27. So you added it 3 times, you got to 23, right? I had 3 common differences in there. It looks good, right? There's my common difference of 9. Works out perfectly. Now that I know the common difference, let's go back and find out what that first term happens to be. We can reverse engineer this. So here's our formula, right? Tn equals T1 plus n minus 1 common differences. Now, I have 2 terms in this, right? I have 2 terms. I could really use whichever one I want, right? The Tn is basically a placeholder for any term in the sequence. So you could use T4, you could use T7, it won't matter. I'm going to choose T7 to use because the number's positive, right? Negatives sometimes cause a problem for some people and we forget how to deal with them, so let's stick to a positive one. So I'm going to say that T7 is 23, right? So therefore, this means that if I plug the information I know into this, let's do this formula in terms of T7. So 23 equals my first term plus, well, I'm using T7, remember, so n is 7, minus 1, the common difference is 9. The only variable left is T1, which we can now solve for. So 23 equals to our first term plus 6 times 9. So 23 equals T1 plus 54, which must mean the first term is equal to -31. So remember what I said earlier, that those term values can be negative, but the number that can't be is the term number. You're never going to see something as term -2, right? But term 2 could be equal to a negative. That's totally okay. So just make sure you keep that in mind. So there we go, we could solve for it depending on the information we're given. All that looks good, but what happens if there's variables in your sequence? And what happens if they're not specific numbers anymore? Does anything change? And the answer is no. right? This happens exactly the same way. So determine the value of x such that x plus 2, 3x minus 1, and 2x plus 1 form a sequence, right? They're the first three terms of that sequence. Well, we got to think about what to do here. There's a lot of variables. Now, if this is an arithmetic sequence, they have a common difference. So there is something that these terms have in common to get from one to the next. And the goal is to figure out what that is. So if I just label this first, let's call this one T1, there's T2, there's T3. It gives us a way to talk about them. So let's take the second term and subtract the first term. Right? This will allow us to find the common difference that exists between them. If I know that, then I can find the common difference between the next two, and since it's a common difference, those differences should be equal to each other. That'll give us a way to solve for our variable. So let's do some subtraction here first. So we'll do 3x minus 1 minus x plus 2. Be very careful. You're subtracting that entire expression, so the brackets are important here. So 3x minus 1 minus x minus 2 is what it works out to be. The sign changes because you're subtracting that whole expression. Collect your like terms. So that common difference from the first term is going, for the first two terms I should say, 2x minus 3. Right, so there's a common difference, but also that common difference could be found by doing T3 minus T2. Remember, as long as you pick two terms that are consecutive, take the bigger one, subtract the smaller one, or the next term from the previous one. Bigger, smaller may be a poor choice of words because, well, values could change. So let's subtract those ones. 2x plus 1 minus 3x minus 1. The bracket thing is the same as before. So 2x plus 1 minus 3x plus 1 this time. So this common difference works out to be negative x plus 2 when you collect your like terms. But I have two different expressions that represent the same thing, which means that those common different, let me color code this actually. Those common differences should be equal to each other. So the one in blue should be equal to the one in red. So 2x minus 3 needs to be equal to negative x plus 2, right? They are a common difference. They have to be equal to each other. So I only have x's in there. It's one equation, one variable. We can solve for it quite easily. Collect your like terms all together. Whatever side you put it on doesn't matter. So I'll put my x's on the left. Right, so add an x to both sides, there's 3x. Add this blue 3 to both sides, you'll get it equal to 5, which means now your value of x is 5 over 3. Right, divide that 3 on both sides, and there you have it, 5 over 3. So without the numbers in there, we can still solve for that value, remembering that there is a common difference. So there is still a way to relate terms to each other, even though they're variables. That is also possible. Other thing we're asked to do is to determine the numerical value of those three terms. So I know that term 1 is x plus 2, which means, well, I know x is 5 over 3 plus 2. So you can add that fraction together however you choose. We won't spend the time talking about adding fractions. But when you do add them, you get 11 over 3. If you do the second term, so T2, that was 3x minus 1, which means, oops, that's equal to 3. 5 over 3 minus 1. This one's nice. It works out to be 4. Okay, because the 3's are going to cancel out. You're really just left with the 5 minus 1. And then our last term of T3 is 2x plus 1. So 2 times 5 over 3 plus 1. That one works out to be 13 over 3. There's your third term. Okay, so there we go. Not necessarily that the common difference is 5 over 3. That was just what x happened to be. We weren't even asked to find the common difference. If you wanted to, you could take your 5 over 3, that was x, plug it into either of those red or blues to find out what your common difference was. You could do that way as well. Okay, the last one on here before we come to a close talks about, a couple comments. right, in some of their sequences and patterns that happen. So some comets are called periodic comets because they appear regularly in our solar system. Comet Kojima appears every 7 years. It was last seen in 2007. Halley's Comet, or Halley's Comet, I don't really know how you say it, one or the other, appears every 76 years, last seen in 1986. Determine whether or not both comets should appear in the year 3043. Okay, there's a lot of information to digest here. So we got to look at two cases, right? There's two comets. So let's think about doing, let's do Kojima first. We'll do that one in blue. Kojima, there we go. Now, if we're going to think about a pattern here, well, Kojima appears every 7 years. We're talking about arithmetic sequences. So if it's 2007, if I add 7 years, I'm going to see it again. If I add 7 years, I'll see it after that. So I know this is arithmetic. So that common difference here is going to be 7 for that pattern. Well, the only information I have on the last time it was seen was 2007. So let's start our pattern there. Right, we'll start it at 2007. And the term that I'm looking for, the year I want to make sure that is part of this pattern, is 3043. So if 3043 is in here, it will have a natural term number, right? It's going to be a whole number that's positive. If I can solve for n and it ends up being a positive whole number, counting number, when that term value is 3043, then yes, it will appear in that year. So I'm looking for n such that it's a positive whole number. That's what we want. Okay. So let's do that one first. Knowing all that information, here's our formula. Right? Take your first term, add to it n minus 1 common differences. So fill in what you know. I know the value we're trying to locate is 3043. I just don't know what term it happens to be. That's what we're going to find. So the first term is 2007 plus n is unknown minus 1, d is 7. Okay, so you can subtract 2007 on both sides first if you want. Doesn't really make a difference how you look at it. Make sure I did that correct. I got term 1 as 2000. Looks good to me. So let's grab our calculator. So let's just subtract. So 3043 minus 2007 moves that over. So 1036 should be equal to n minus 1 times 7. So 1036. Oh, let's just, how do I want to do that? Let's distribute first. Not sure how I want to do it. This actually would work better. So we'll add 7 to both sides now. Add a 7 to it. 1043 equals to 7. And last step is to divide by 7. And I got 149. I think I did something that doesn't... What did I do? I put something in a wrong spot, I think. Let's double check here. D7. Actually, I don't think I did. Okay. So I get 149 equal to n. Interesting. Okay. And let's go check out the other. Yeah, okay. Seems okay. And let's move this. Alright, interesting. My key is telling me something different. Anyways, that's okay. Let's check out Halley's Comet. So that one appears, says every 76 years instead. So there's our common difference, 76. All the same reasoning from before is still true. Last seen in 1986. So there was the, well, for our purposes, the first time we're going to include it in our pattern. And again, we want to find out if 3043 is going to be in that sequence. Because if it is, we're looking for a whole number, term number. So let's try this one. Tn is T1 plus n minus 1 differences. So Tn is 3043. T1 is 1986. plus n minus 1 differences. And the differences is 76. That's our difference. So let's move the 1986 to the other side. My calculator over. So 3043 minus 1986. 1057 is equal to n minus 1 times 76, which means 1057 is equal to 76 n's minus 76. So we'll add a 76 to both. 1133 equals to 76 n's. Divide both sides by 76 now, and I end up with a decimal for n, which ends up being a problem. Right, so this ends up being 14.907 something something for n. Right, which is an issue. If the comet is supposed to appear in that year, well, my term number shouldn't be a negative, or shouldn't be a decimal. Right, I'm not going to be able to add 76 to it 14.9 times. I either add it 14 times or I add it 15. There's no in between. So here now I know that if 3043 is a year where, so if 3043 is a year the comet appears, n should be a natural number. Right? N should be a natural number. So I know that Kojima will appear. I know that Halley's Comet will not in that year. I don't know what other year it will appear, but I just know in 3043 one of them will, one of them won't. Okay, so there's your little quick introduction to arithmetic sequences. We'll talk about series later on in a future video, so look out for that one. In the description box you'll find those two links, one of them with the blank copy of everything that we did, one with the solution, should you just wish to look at that. But I feel like, if you've been here before, you know that already. So we'll see you in the next one.